Hello, everyone. My name is Ion Powell, and today I will be presenting on a machine learning architecture that can take phase field models, take the data, and then replicate them. So, first, what is phase field modeling? It's when you take a set of partial and ordinary differential equations and you are able to estimate how these phases evolve in time. In particular, we have the Cahn-Hilliard equation here to estimate spinodal decomposition, which is a common benchmark problem due to its simplicity. The inputs into this are the concentration of each phase and the phase's mobilities. Now, why would we want to make a surrogate model of this? Well, because when we are exploring massive phase diagrams or complex systems, we want to have some sort of estimate as to how well certain areas will perform or what the microstructure will look like. In particular, we can look at high entropy alloys in additive manufacturing. Running those phase field models can be very expensive due to the fact that we have to run numerical methods to solve them because there is no easily accessible analytical solution. So, different machine learning models have been developed to tackle this. One of the methods discussed in this paper is the autoencoder plus deep ONet surrogate. So initially, we have a convolutional autoencoder. We have different convolutional layers that takes in the microstructure data and then puts it into a latent space. In this case, there's 196 different latent points here in the final model. And then from those 196 values, it can actually transpose those values back into the same microstructure. After that was done, now we have a latent representation of the microstructure, and you can train what's called a deep ONet on that, where you have a branch network and a trunk network. The branch network takes in the actual microstructure data and then maps it to 1,960 variables. And the trunk network does the same, but for the time. And then you have this operator, G. That operator is now able to estimate what the next step in the latent space will be for a given step. Not just the next step, but it can also estimate even further in time. We can see what our microstructure looks like as what the input data is, and then what it looks like after it's been encoded. The microstructure here is mainly ones and zeros with some of a gradient right here, because that's how phase field models estimate gradients and energies, is by saying we have somewhere from -1 to 1. There's a slight gradient between them. But this can be tricky to train a machine learning model on. When you put it into a latent space, now we have a smooth set of data that can be trained. Principal component analysis was looked at for this and was used in previous papers by the same authors, but it worked on the spinodal decomposition paper model in the past because there's linearity within it. However, that does not work for possibly future equations that this needs to be applied to. So this is looking at different methods. The autoencoder architecture is as follows. It's pretty standard. I just want to bring attention to the latent dimension here in the center. That's our 196 points. And then now we can take a look at the deep ONet. As described before, you have your microstructure data here in the function, and then you have the time here. So you have your branch net. This is a stacked deep ONet. This is what's being used here. You have your branch net and your trunk net, and together they create an operator that can predict for a different time and a different set of microstructures. You can see that put here. Now the deep ONet architecture changes the loss function and for how many latent dimensions you have. The loss function doesn't change, the error changes. And the error improves as you have more and more latent dimensions. And the researchers here tried different architectures and just chose the one with the lowest error. Now, the surrogate accuracy is impressive, but we can see here's our true microstructures here at the top. And the predicted microstructures are very close. However, it's missing these smaller spots. So what's happening is there are different scales of evolution over time for this model. Early in the model, there are more small dots that survive, but late in the model, they have combined with the other phases. So what the researchers did is they weighted the earlier time steps more in the training process so that it would capture these smaller dots. And we can see here that the exact same thing. The error is higher for the lower time steps with the surrogate model. And then as you go further in, it's more accurate. And we can also see that here. This is the extrapolation for time steps that haven't been looked at by the model. And we can see an increasing error over time. So what they did is they put more emphasis on the earlier time steps, and we can see it retained some of that information. And we can see here that there was a hybrid model that was used. Memphis is the phase field modeling proprietary software at Sandia. Sandia was a big proponent of this paper. And we have our true microstructure here on the left, the predicted microstructure, and the pointwise error. And we can see now that the predicted microstructure is now overcompensating for that small phase. We can see here in the true microstructure, that small phase, it disappears. It's completely gone by this time step. However, the predicted microstructure is retaining it for another 2 time steps. And we can see that here in the error. We can even see here that it's over predicting those. So that's probably the biggest room for improvement with this model, is how do you tune in exactly how much weight you give to each section of the time dependency. And the time improvement was very impressive from this. There's a 28% improvement in time because T1 and T30, you use, for the first 3 steps, you use the more expensive method. It took 135 minutes. And then you say, oh, T30 to T40, that usual 45 minutes was now taken down to 2 seconds. In total, the savings was about 28% here. But this model is still overrepresenting the early training data. If you only care about the late stages, that's okay. It still did pretty well. The accuracy at the end was decent, but there's definitely room for improvement. So an autoencoder was trained on a large phase field data set to recognize how the latent space evolved with time. And we can see that we have a smooth continuation rather than ones and zeros with a very slight gradient. That's very useful for training a machine learning model. And a deep ONet surrogate was trained on the latent space to learn an operator that maps the microstructure over time. This gives us the prediction capabilities that we saw here. And then the surrogate model struggled with time dependency, and manually changing the weights of the time region resulted in errors. So my biggest question from this paper is, how do we go forward with training the weights in a way where it can automatically determine, hey, we need to give more weight to this area and more weight to this area? One of my thoughts on that is perhaps for the trunk part of the branch network, the trunk part is the one that takes in the time, maybe have some sort of Gaussian distribution over the network itself. So for different time points, it's specifically looking at a section of the neural network rather than the entire neural network, which would encourage the neural network to specialize different areas of its brain. Yeah, that's the paper. It's very interesting. And I'm excited to see where this goes next, because this is part of my future research. So thank you.